On Monday, we'll have a quiz over substitution reactions and mass spec. We need to pick up the pace a little bit. I think that's it. Good to go? Okay, sulfur is a good nucleophile. Your body uses that a good bit. A couple of examples there. Let's look at nitrogen, amines. Direct alkylation of amines. Okay? Talking about either ammonia or alkylamines. Amines that already have one alkyl group. Importantly, no need to form an anion in this case. Because the neutral nitrogen of an amine, sp3 nitrogen, it's a good nucleophile even in the neutral state. It does not have to be an anion. What are good nucleophiles? Anions, or what? sp3 nitrogens. sp2 possibly reasonably good, but not as good as sp3. Okay, sp3 nitrogens can be ammonia, or it can be an alkylamine. Here's an example. Ammonia here, good nucleophile. We have a carbonyl leaving group over here. Okay, one of the problems with this reaction is direct alkylation is that it can over-alkylate, polyalkylate. You end up with more alkyl groups than you want. Let's look at just alkylation. Ammonia, good nucleophile, neutral state. Come in here, kick off the leaving group. What do we get? We get this. That's condensed. But the nitrogen is now positive because it now has 4 bonds. Previously in our reactions, the product was all neutral because we went from anion to neutral. Here we went from neutral to cation. Plus Br minus, the leaving group, right? Makes sense. We just did SN2. Okay, we can go neutral here by removing a proton. What can remove a proton? Can Br minus remove proton? If it did, just acid base, leave lone pair on nitrogen. We would get that. Plus HBr. Problem is that equilibrium is not favored. It's no good. Okay? This is just going to come back this way. Because that's a strong acid. It's going to protonate this and it's going to exist like that. You can look at pKa's. Okay? In the end, Br minus is not going to remove an H. So it's not going to go neutral unless you include some type of base. A variety of bases have included in this reaction. You can either include it in the reaction or add it after the reaction to take off the H. Br minus will not. You have to include some other type of base, such as potassium carbonate, 101 bases. You can get final product. What have we did? What have we done? We've added what to the nitrogen? An alkyl group, right? An ethyl. So we have alkylated the nitrogen. And it's a direct reaction. You have not seen an indirect yet. Okay? Direct alkylation of amines. That's what we just did. Understanding the ions, Br minus, okay, chemistry. How do you get polyalkylation? It's a very common side product, unwanted. It's one of the problems with direct alkylation. You can end up with not one alkyl group on your nitrogen, but 2, when you did not want to. How? They can alkylate again. Well, not this guy, because it has no lone pair. But we can get the product here in this reaction a couple of ways. Either the base, if we included it, can form that. Okay? Or if we don't even have a base, ammonia could take the H. Because ammonia is here. Instead of just reacting here, once this is formed, ammonia can start coming over here and taking the proton. If it takes the proton, it frees up the product, but now the product can come in here and react again. And after you remove proton, you get polyalkylation. And you can't stop that from happening. That is, you can't say, hey, once this is formed, ammonia, don't take the proton. It ain't going to listen to you. It'll take the proton. And once you get this, it's not just going to sit there. it's going to compete with ammonia to react with this. You can't say, hey, I don't want you to react with this. It ain't going to listen to you. So all this can happen, and you can end up with 2 alkyl groups when maybe you only wanted 1 alkyl group. And that's a common problem with direct alkylation. Okay, you got all these equilibrium going on in the same reaction in the same round bottom flask. Now, it's a problem. Sometimes this reaction works okay. If you look at the very back, synthesis of Zyrtec, it shows direct alkylation of amines. I'll refer to this later. At this point, I reckon let's look at 43 going to 44. What's going on? You got this secondary amine. It's reacting with this here, with the chlorine. This is attacking the carbon, yeah, kicking off the chlorine. And we get this bond form. It happens to have an OH over here. So that is a direct alkylation of an amine. And they're getting very good yield. And the H has been removed. What removes the H? Triethylamine. They're using triethylamine as a base to remove the H. And they're doing a direct alkylation in good yield. So it can be done. The polyalkylation is a problem sometimes. While we're here, let's go ahead and look at this top reaction. It's another direct alkylation. What do we have here? We have this compound here. They're actually doing 2 steps, and they're not showing the product after the first step. And they're getting this here. What have they done? Nitrogen has replaced the bromine, the leaving group. This nitrogen right here. By the way, this compound has 2 nitrogens. Which nitrogen is nucleophilic? One on the left. Correct. Because the one on the right is conjugated. Okay? This is attacking, well, hold on. What's the mechanism? I say SN2 most likely. If it's SN2, this is attacking here, kicking this off. Can you do SN2 on this carbon? Secondary. You do SN2 on the secondary. The second step removes this group here. Okay? That's how that group got removed there. We won't worry about that. That's a direct alkylation of the nitrogen. The first step, when they're doing this, they include sodium carbonate in the reaction. What's the purpose of the sodium carbonate?
And the base that
You showed on that previous page, a base to remove the proton, because, again, they're not showing the product, but in the product, the H of this nitrogen is gone. That H is gone. It's removed by the carbonate, explained on the previous page. Xylene is the solvent, reflux 10 hours. Okay, I said it's most likely SN2. How would you confirm that it's SN2 and not SN1?
Could change the concentrations of the 2 reactants.
Okay, you can change the concentration of the reactants. Which reactant would you look to change?
Well, if you change the electrophile and the nucleophile and it affects it, then it'll be SN2.
Uh-huh. I would only change the concentration of the nucleophile. Okay? Change the concentration of the nucleophile, that is, repeat the reaction. You can determine rates. Repeat the reaction, maybe double the concentration of the nucleophile, What if you double the concentration of the nucleophile and the rate then doubles? What does that tell you about the mechanism?
SN2.
Must be SN2. What if you double the nucleophile and the rate stays the same?
SN1.
Okay. Yes. What about just substitution pattern here based on this? Would it be SN1 or SN2? The leaving group's on a secondary carbon. SN1 or 2? Be either. If the leaving group was on tertiary carbon, it would be what?
SN1.
SN1, because you don't do SN2 on tertiary carbon. But it ain't tertiary carbon, it's secondary. Okay? Yeah, rate would be one way. Another way would be possibly, this is chiral. That's a chiral carbon, yeah? Because this ring is not the same as that ring, that's chlorine. Now, there's no stereochemistry shown here, but what we could do is we could do the reaction with stereochemistry. For example, we could do it, if we could get our hands on or make only R there, then we could do the reaction and see what stereochemical outcome we got. If we did the reaction and we started with R and we ended up with only S, that would tell us the mechanism was what? SN2, backside attack, conversion. But if we started with R and ended up with racemic, that would tell us the mechanism was right. Why does it matter? Well, if you were working for this company making this drug and you wanted a better yield, for example, what is that, 77.2? I mean, 80, 87 would be better. More yield, more product, more money. Yeah? And the goal was to improve the yield. You need to know the mechanism, because if the mechanism was SN1, you'd be wasting your time by adding more nucleophile. You'd be wasting your time and your money. And so you want to know the mechanism if you're going to try to modify your reaction. Okay. All right, throughout organic chemistry, there are alternative approaches to direct alkylation. Indirect methods. I'll show you one here. We'll see at least one or two more in organic too. Okay? Same type of product we made on the previous page. But here it's going to be much better yield and we're not going to get polyalkylation. One way to do this, instead of using the amine like ammonia, we can use sodium azide. What's the charge of the N3 here? Yes, negative. Okay? And by the way, on week 1, I asked you to do a Lewis structure of sodium azide, or HN3. It was in the workbook. Okay, N3. Lewis structure is, that's positive, that's negative. Both ends are negative. Okay, that's N3, but it's -1. Sodium can sit with it. Either end is nucleophilic. These electrons can attack here, kick off the bromine, and you now have N3 bonded to the carbon. Again, you can draw a Lewis structure there. Azide. Azide's a good nucleophile. Okay? Azide's also a little, you gotta be careful with azides. They can be explosive under certain conditions. They can also be skin irritants. Very allergic responses to azides are possible for some reason. But in the textbook, it's pretty safe. All right? You get a good yield of this. There's not going to be any polyalkylation. The other end doesn't alkylate. Because once it alkylates there, the rest of it's net neutral and becomes much less reactive on the other end. Now the N3 can be cleaved with hydrogenation. You can cleave off 2 of the nitrogens and you can get the primary amine, Okay? It is going to be a primary amine. I'm not actually sure what the fate of the other two nitrogens is.
I don't think it's nitrogen gas. I think it's probably some reduced nitrogen.
But you can make primary amines this way. Where on the previous page we made the same product, but the previous page had the problem of polyalkylation. Okay, because that was a direct reaction of ammonia, direct alkylation of an amine. This is called an indirect method. You're not really reacting an amine. The azide is serving as some sort of a surrogate. All right? One of the main reasons to show this is just to introduce azide, okay, and the idea of an indirect method. We'll see other indirect methods in organic too. Okay, quats. You ever heard of a quat? Typically refers to a nitrogen quat. A quaternary amine salt. This here. You know, you have primary, secondary, tertiary amines. You can also have a quaternary amine. That means the nitrogen binds to how many carbons? 4. Right here, bonding to 4 carbons. And the nitrogen is thus a positive charge. Okay? Called a quaternary amine salt. Sometimes it's called a quat. And you can have a quaternary carbon, but, all right? It's ionic. But these are final products, and these are used in certain cases for things. One case is antimicrobials. Okay? This quat here, which by the way, it's got 2 decyl groups, 10 carbons, so it's didecyl, dimethyl, ammonium becomes a positive nitrogen we call ammonium. Didecyl dimethyl ammonium chloride. All right. It's a common antibacterial. You ever been over to the YMCA or the weight room area? They have these things on the wall where you clean your hands. All right. Next time you're over there, look at the little label. All right. The label says that right there. All right? That's why I put that one there, because I thought one day I'm like, okay, I'll put this on my hand. All right? Quaternary ammonium salts are used as antimicrobials. They somehow kill microbes. All right? Maybe some of your hand sanitizers in your pocketbook has it, yeah? Yep. Another important quat, choline, which you'll see in biochemistry, is actually a quat there on the nitrogen. You ever heard of acetylcholine? Or acetylcholine? Yeah, neurotransmitter? Well, that's just choline with an acetyl group on the oxygen. Okay? But the choline part has a quaternary ammonium. All right? How do you make these? Well, you're just alkylating the nitrogen. For example, you can take this tertiary amine, react it with such like this and heat, and it will alkylate again. It's a little tough. You have to heat it because it's tertiary. It's kind of sterically hindered. But it will alkylate again. You kick that off, and there you go. There's no proton to lose. Br minus wouldn't take the proton anyway. So it just sits like that. It's an ionic product. It's a salt. All right, called a quat. It just comes from an SN2. One interesting quat is the world's most bitter compound. World Records in Organic Chemistry. It's a great book. All types of interesting things. World's most bitter compound is this compound right here. It's a salt. Ion pair. It's a quaternary ammonium salt. And the anion is not just Br minus or something, it's a polyatomic, it's an organic anion. Benzoate. That's a salt.
And it's apparently the world's most bitter compound. It's used, that compound is used to put in things like antifreeze, to keep like pets from drinking it. But otherwise, pets will drink antifreeze and no good. Even small children, because antifreeze has a little sweet, good taste, but it's deadly toxic.
And so such can be put in there. Then when the cat goes to drink the antifreeze, it goes, I'm drinking that. Yeah? What about carbon? Well, most carbons don't have a lone pair, right? So most carbons are not going to be able to act as a nucleophile. But we can generate a lone pair. And one that we have done is with terminal alkynes. Remember, the terminal hydrogen is somewhat acidic. We can generate the alkyne. Anybody remember a base we used to do this? Because whenever I showed you the bases, I said, well, that was at the end of organic test 2. We ended with test 2, generating these anions. And the comment there was, we'll use these during test 3. Well, now we're going to use them. But how do we generate them, though? What base do we use? Like N-butyl-lithium. We also used NaNH2. Okay. Look at the alkyne handout, the last page. And then we talked about the miner's helmet, the reverse reaction, generating, putting the H back on. Okay. We can make the acetylide anion. But now we have a good nucleophile. Now this will come in here if we have a carbon with a leaving group and kick it off. And the product would be boom. Up there? Is that right? We got a little stereochemistry here. Hold on. We didn't magically lose the deuterium. The deuterium is there, yeah? Because the leaving group is the tosylate, right? Deuterium is just a fancy hydrogen with an extra neutron. SN2, right? Did we get it right? Look good? We get the stereochemistry right? My product? Why going back? It is inverted. Is it not? It's inverted. I mean, the ethyl and the deuterium are over there like this. Okay? Right? They're both going that way. This comes in, they straighten out sp2 planar transition state. And then when the tosylate leaves, these bend this way to replace. So these two are now over here. It's still forward. The ethyl's forward, right? Goes planar. And then it comes this way to make room, but still forward. That is inversion. Don't fall into the trap of this is bulls and that's got to be dash. That's inversion. The leaving group is in the plane. Okay, the plane, right? Leaving group is in the plane. So if the leaving group is in the plane, I mean, it's really like this drawn, all right? It's a little bit up. See how it's a little bit up? So how does the nucleophile come in? Well, it comes in from over here, right? Right? It's like opposite. and any groups on this carbon, if this group is forward, like the ethyl, what does it do? It just comes this way, but it's still forward. It's inversion. All right, we can do RS. Oh, that's a little complicated because you got priorities are mixing up. What is this here? RS. Oxygen 1, carbon 2, D would be 3, H would be going back. That's 4. Is that right? What is this? S? What is this? This is 1, that's 2, that's 3. H is still back. What is this? R. That doesn't prove it's inversion though. But for us it pretty much does. What proves it inversion is you know that the nucleophile comes in backside. Okay, need to look at that some. Happy birthday. Thank you very much, whoever drew that. If you look at the handout that I gave you about mechanisms, when we first, probably during test 2, okay, when we showed 2 different ways to make nucleophile carbon bonds, at the bottom of that handout it showed inversion different ways. Okay? The leaving group is in the plane. All right. KCN. Cyanide. B. That must have been A. Cyanide right here. Yeah? You look at the little structure of cyanide, got a carbanion. Potassium cyanide, sodium cyanide, very common. DMSO is a common solvent, polar. It's on the solvent page from one of the first handouts. Carbonyl-nucleophile, boom. Come in here, kick this off. And products. Phenyl, boom, boom, and we can just show the cyanide as CN. It's going to be bolded, right? Now here we went from dash to bold. Because the leaving group is back. And so the nucleophile comes in from the front. And so that's why it's bolded. And the backbone is the same though. But again, in the previous example, the leaving group is in the plane to the right. So in the product, the leaving group is in the plane to the left. But you got to realize that the groups just do this. This hand is still forward when it inverts. Hand facing you, hand still facing you. Okay? This is more common, cleaner. Guess what? If I showed you this all class and never showed you that, then the next class when you see that, you're not going to be able to deal with it. So just take the time to understand the stereochemistry of it. More straightforward here. Good? Use of cyanide is a good nucleophile. KCN. Y'all remember a band back in the 1970s? KCN, the Sunshine Band? KCN, the Sunshine Band. Okay, proving mechanism by product regiochemistry. Let's look at this reaction here. We take this compound and heat it in ethanol. This ethanol on heat. We get 2 regioisomers formed, plus HBr. What's the mechanism here? First off, it is a substitution, right? Because if you just look at this, the O-ethyl is replacing the bromine. It's a substitution. You know 2 substitution mechanisms. Which mechanism is this?
SN1. How do you know it's SN1? Leaving group is not on tertiary carbon. What?
I was looking at the product.
I don't know how that's going to help you determine mechanism. It's on tertiary. What do you mean?
Yeah.
It looks like we got a rearrangement. How did we get the second product? Okay, and a rearrangement's only going to come from
SN1.
Carbocation, SN1. Okay.
what type of nucleophile do we have here?
It's neutral.
Weak or strong?
Well, strong is an anion or sp3 nitrogen, so this is
Weak. Since it's weak, what mechanism? Remember, SN2 requires strong nucleophile. We don't have a strong nucleophile. Mechanism is SN1. But also the fact that we got a rearranged product tells us it's SN1 because rearrangement comes from carbocation. Let's show the mechanism here. What's the first step?
Working these.
First step of SN1,
Working these.
leaving group just leaving. That leaves to give this here. That's your rate determining step for SN1, carbocation formation. Can a leaving group just leave? Yes. What happens if you put HCl in water? Essentially, this leaves to make H+. Now, we know it's really not purely ionic, but the Cl-, I mean, it's really H3O, but the chlorine becomes Cl-. It essentially leaves. Well, it can also leave a carbon. Now, it's not going to, it depends on different things. A little heat helps it leave. But also the substitution pattern. What type of cation did we make? Secondary. If this was tertiary, it would leave faster. But secondary can still leave and make that. You would not want to do primary, right? Primary carbocation's bad. That's probably one of the, if we can say 5 things we should learn in organic 1, primary carbocations are bad. That probably should be on the list. Okay? Secondary is okay. Here we go. How do we get the first product? Ethanol. Okay? Can act as a nucleophile, but it's weak. You see, ethanol is not strong enough to come in here and kick that off. That's a more difficult process. And ethanol is not strong enough to do that. It's lazy, it's weak. But if we showed a carbocation, now it will sort of like, okay, I'll react with this. And that gives what? We have oxygen with an ethyl and an H, and a lone pair and a positive. Note, some of you guys will want to remove the H and make a minus here. Okay? No. Ethanol is not ionic. We do not have a strong base here to make the anion. No. Neutral ethanol is the nucleophile. It bonds to the carbocation, making this intermediate here. And then we can get this product by what? We see that HBr is formed. Br minus can now take the H. Get there. See, it will take the H from an oxygen. Where you remember earlier, it would not take an H from the nitrogen. The bad equilibrium. Because nitrogen is basically a base. It's going to come the other way. But this will happen. If you do this reaction in heating, you may have some vapor coming out. Probably HBr. And if you hold some pH paper above the reaction, it'll probably turn red. The HBr will be driven out, especially if you're heating. Okay. How do we get the other product? Well, what are carbocations prone to do? By the way, what do we need over here? Looks like we need that cation. Does that look right? How do we get that cation? Hydride shell, yeah? Why is this cation better than that one? Tertiary. And then you can get home from there. We attack, okay, multiple arrows, however many it is. I'm not going to do it the same as over here. You can finish that up. If we had to predict a major product, which one would we say is major? Remember we said if you can rearrange, we always are going to do that. And rearrange to a better cation. The fact that we got regioisomers tells us it's SN1. That's the only way you're going to get regioisomers. SN2 does not give regioisomers. If it was SN2, the nucleophile would be on that carbon only. Of course, the fact that we're using a weak nucleophile also tells us it's SN1. SN1 is largely a carbocation mechanism. Okay? And once you get your carbocation, it's then a lot like our alkene reactions were. Because we did the same type of stuff when we did alkene reactions. You can get carbocations from alkenes. You can also get carbocations from something with a leading group, where it just leaves. Same reaction down here, but with stereochemistry. Please take a look at that. How would the stereochemistry be if we included that? By the way, this is going to be called a solvolysis reaction. Because all we did is we took a substrate and we just heated it in what is usually just a solvent. Now usually solvents by definition don't react. But here it did. And when it does, we call it a solvolysis reaction. What is the rate equation for the above solvolysis reaction? That would be rate equals what? Some type of constant times what? Times the alkyl halide? What was it? Chloride, bromide? Yeah? What type of nucleophiles react strictly by SN1? Weak, the opposite of strong for SN2. Summing it up here, guys. Substrates with leaving group on primary carbon only undergo SN2. Why? Because you'd never make the primary carbocation. And so you'd never do SN1, correct? Substrates with leaving group on tertiary carbon only undergo SN1. Why? Because you never do SN2 with leaving group on tertiary carbon. I think we put at least 3 exclamation points on that comment. Substrates with leaving group on secondary carbon can undergo either. If you're leaving groups on a secondary carbon, you're going to have to look at something else to determine the mechanism. Like strength of nucleophile, like was the one above. Or maybe there's other information that you need to look for. With strong nucleophiles, the reaction will always be bimolecular. For substitution, that means SN2. But it can also be E2. And that's the next handout. Both of those are bimolecular. With the weak nucleophiles, which are lazy, reaction will always be unimolecular, like we just did. SN1 or E1 once we do elimination. As long as the substrate is secondary tertiary. Because you do not do a unimolecular mechanism on a primary substrate, primary ligand group. That was just a repeat of what was stated up here. Of course, if the substrate is primary, the reaction will have to be bimolecular, right? But of course, a bimolecular reaction with a weak nucleophile will be quite difficult. That's summing it up. Okay, there's some practice over here. Not the first one. Show a product here, including stereochemistry. All right, these reactions, if you haven't noticed yet, you got to assess them more than the alkene reactions. The alkene reactions we had, you have like a certain reagent, okay, that looks like it's antimicrobial conhydration. A little memorization. Here it's more of an assessment, okay? I can give you a million different reactions, and there's a way to assess it. And then you can do a million different reactions. The same questions to ask, okay. So, can someone propose a product here?
Racemic alcohol.
Yes, it's going to be racemic alcohol. Plus what, if you want to balance this out? HBr. Okay, what's the mechanism? SN1. Why is it SN1? Weak nucleophile. What's the rate determining step? Leaving group leaving, make carbocation. And then the water attacks the carbocation. Which side does it attack? The carbocation is planar. Either side. That's how you get both R and S. That's what racemic means, right? 50-50 mix of both R and S. So the product is chiral. Okay, it's got a chiral carbon here. Okay, how about the one on the right?
The reverse stereochemistry.
What is that? S? Yeah. SN2. And just like Big Mac comes with fries, what does SN2 come with? And here, do we make carbocation here?
No.
Why not? We made it over here. Why do we not make carbocation over there?
Anion, strong.
I mean, it's the same substrate. Why not? Explain why not.
Strong nucleophile anion.
Yeah, it's strong, but why doesn't this make carbocation? With what? Yeah, but again, why does it not make carbocation?
It's strong enough to kick off the leaving group.
Yeah. Well, what I'm trying to get at is it's just rate. This leaving does take a little bit of time. It's the rate determining step. It takes a little heat. Okay? What's going on here is before this thing can ionize, This thing, strong, here I come, I'm kicking you off, you ain't got time to ionize. I'm a bully. It's faster, it sort of implies that process is easier than the ionization. But the reason that's easier is because you got a strong nucleophile. It's like, here I come. I'm a bully. I'm kicking you off. I'm not waiting. See, over here, water's lazy. Water's just sitting there on the sofa. Only thing you can do is ionize. But over there, here I come. Get out of the way. I'm here. Okay. Backside attack. You don't have time to ionize. That's the difference. So this goes SN2, and since it's backside attack, you get inversion. Yeah? Okay. Product here.
Is there waste in it?
The only difference is this it's the same neutral nucleophile. We're going to get what mechanism here?
SN1.
We get this ether. It's going to be racemic. That's chiral plus what? Plus HI. You should be able to do the mechanism. I minus takes the H, so the oxygen can go neutral. It's a substitution reaction, but it's SN1. Okay? Weak. SN1. Weak, SN1. Racemic, yeah? How about the one on the bottom right?
SN1.
On the bottom right?
SN1.
Why SN1? Is the nucleophile weak or strong? Strong. And if you look at the previous page, it said if the nucleophile is strong, it's always bimolecular. Because strong is going to put its nose in there and be involved in the rate determining step. It's going to be thus bimolecular. I want to be involved too. I will be involved. It will be involved. So what's the answer? Strong, not SN1. What's the answer? But it's a tertiary, but the leaving group's on tertiary carbon, and you don't do SN2. The answer is neither. The answer here is E2. Classical E2. Yes, bimolecular, like we said. But not SN2, because you don't do SN2 on tertiary halide. This takes us into elimination handout. That's a classical elimination reaction there. Okay? There's others to do below. I'll send out answers to the first page and to these. And we'll be moving on to elimination after the quiz on Monday. Good to go? Lab upstairs this week. Upstairs. Double E2 elimination.